Today I'd like to talk a bit about lossless still image codecs. So the question might be, why examine these? Well, there have been some interesting advances going on in the last 3 decades. Coupled with this are continued improvements in sensors and the new computational requirements of evolving 3D, multispectral, and high dynamic range workflows. Here's a list of the codecs that I looked at, starting with JPEG's original lossless compression from 1992. Yes, the original and ubiquitous JPEG standard has a little-known lossless option. In fact, it's in use today within DNG. Next, I looked at JPEG LS, which is utilized in Artec Studio among other current programs. This was followed by JPEG 2000, an archives favorite, and Microsoft's JPEG XR. Finally, FLIF, PIC, and JPEG XL are all modern codecs that continue to push codec design boundaries in ways that I felt deserved attention. Along with these, there were a few alternatives that didn't make the cut. I won't go into this in any great detail other than to say that all of these have at least one weakness when it comes to potential application in cultural heritage archives. A brief note on what this study was not. Though these aspects were considered in putting together the final list of examined codecs, the goal here was not on being a traditional compression shootout among encoders or an evaluation of sustainability factors among formats. Sure, there was benchmarking, but there was also an examination of source information content and a look at compression techniques as they may work in the context of information content. So in essence, what I'm talking about here is how we may characterize a given codec's nature and design. Source images were culled from a variety of open access cultural heritage digital repositories and included digitized paintings, transparent film, maps, works on paper, and born digital images. For every codec tested, sets of 3 consecutive encodings were done per reference image. The resulting individual benchmark metrics were then averaged for each compressed test image and recorded as final values to get a more accurate sense of a given encoder's execution across possible fluctuations in overall workstation load and speed. A few words on lossless compression itself. Basically, it aims to reduce redundancy in stored data and increase effective data density. Most lossless methods do this by first generating a statistical model for the input data. The model is then used to map the input to bit sequences in such a way that probable, that is, frequently encountered data will produce shorter output than improbable data. In this way, lossless encoders ignore random data, which has no predictive value and is itself not compressible. I'd now like to take a few moments and talk about this term. In information sources, redundancy is related to information content, which can be described in measures of entropy. The greater the entropy, the less predictable the data, and the more information content. Entropy, in turn, has been thought to provide a numeric correlation to the amount of statistical redundancy within a given source and ultimately the expected limit to which it can be losslessly compressed. Since redundancies in images are directly related to image content, it follows that compression is inherently scene-dependent. Entropy calculations can in turn effectively characterize image scenes and be good predictors of compression potential for given images. However, image file entropy is inherently difficult to interpret and is contingent on how a given calculator models the input. Conventional mathematical analysis tools like MathWorks, MATLAB, and Wolfram Mathematica normally calculate entropy through one-dimensional intensity-based histograms based upon Shannon's classic 1948 formula. A limitation to these methods is that they treat each pixel like a separate observation and do not take into consideration the spatial distribution of pixel intensities throughout an image. For instance, a complete shuffling of pixel locations will yield no change in entropy values when calculated in this way. We know, however, that spatial distribution of pixels can also have a direct influence on resulting compression density. This brings us to a novel measure known as delentropy. Larkin's 2016 delentropy measure attempts to also capture underlying spatial image structure and pixel co-occurrence in source information. For my purposes, I calculated delentropy for all reference images to possibly better understand correlation between an input's information content and redundancy and the resulting compression efficiencies of each encoder. Here you can see how the mathematics get more complex when a second spatial dimension is added to the basic concept of entropy. And for each source image, the previous one-dimensional histograms can suddenly turn into quite elegant 2D gradient maps that you can see on the right-hand side of this slide. For 8-bit source images, delentropy can range between a minimum of 0 to a maximum of 8. Since it was assumed that higher delentropy values would associate with lower compression potential, inverse delentropy percentages were calculated and plotted against lossless compression savings percentages for each codec for each test image. The important thing to focus on in this chart is the shape of the dotted inverse delentropy line, and to think of it as a comparative gauge of information content in each image, the file names of which can be seen along the x-axis. Here I've added the original lossless JPEG and JPEG LS compression savings percentages by image. Again, file names are on the x-axis and the compression savings percentages are on the y-axis. The greater the percentage, the more achieved compression by the encoder. As you can see, JPEG and JPEG LS have similar image-by-image efficiency trends that also followed inverse delentropy estimates. In turn, the data suggests that inverse delentropy may be a good relative predictor of these early lossless codecs compression potentials. However, when I added the remaining post-millennium codecs to the visualization, this agreement between predictor and actual encoder efficiency no longer appeared to exist. Another technique that can be used to estimate the level of entropy in a given image file is to losslessly compress the data to its smallest feasible size using a version of the PAC family of experimental codecs. PAC works by compressing the input file bit by bit using context mixing, that is, mixing predictions from many models at the expense of speed and memory usage. Though no application can describe all possible files and their data optimally, PAC tops rankings on several benchmarks measuring compression ratio. Entropy estimates were thus made by calculating the percent decrease in file size of the PAC compressed files compared to the study's reference files. Since it was assumed that higher entropy values would associate with lower compression potential, inverse entropy percentages were plotted against the lossless compression savings percentages of each codec for each test image. A few observations. Among the more modern codecs examined in this review, all were able to encode images to similar efficiency levels on average and on an image-by-image basis. That these levels also closely followed the pattern of PAC's image-specific inverse entropy estimates, suggests that the PAC tool is a good predictor of the compression potential of such post-millennium codecs. Moreover, as these codecs all comparably approached PAC's approximations for optimum lossless compression, this may be an indication that there is little practical room left for future lossless standards to make further efficiency gains through new designs. And here are the pre-millennium lossless JPEG and JPEG LS results, again for comparison. One of the things that I found particularly interesting in viewing the data in this way was to see how much more variable JPEG and JPEG LS were in compression efficiency from image to image compared to the more modern codecs. What this may indicate is that the post-millennium encoders are better designed to effectively compress a broader range of image types and information sources than their predecessors. This jack-of-all-trades characteristic is sometimes referred to as genericity in the signal processing literature. With this in mind, what interests me in the future is to someday perhaps enlarge the source image dataset that I used in this study in order to see how my initial glimpse at encoding trends may or may not change, and to apply more rigorous comparative statistical tests against the greater scale. Okay, let's now think about encoders from yet another angle. Basic lossless compression schemes primarily do two things in sequence with source images. First, they statistically predict and decorrelate the input data to identify and reduce spatial redundancy. In addition, color transformations from an RGB to a luminance-chrominance color space may also be performed during this initial pre-processing stage. Second, the results of pre-processing are then entropy coded into bit sequences through algorithms such as Huffman coding, which reduces pre-processing statistical redundancies, or arithmetic coding that deals with both spatial and statistical redundancies. In a more general sense, though, data compression strategies involve compromises among resulting data density, speed, and memory use. Computer science describes these associations as space-time or time-memory trade-offs. As a result, benchmarking across these individual metrics can give additional insights into the art and design of a compression software's context modeling, coding, and overall feasibility towards potential real use. Here's a chart of compression savings percentages averaged among all test images and sorted by codec. The experimental FLIF came out ahead of the group, while lossless JPEG was far less efficient. Of note, FLIF, PIC, JPEG XL, and JPEG 2000 were all very close, with JPEG XL being the third most efficient. More on this later. This chart illustrates real-time encoding time by codec, again averaged among all test images. Here we can see how FLIF's compression efficiency comes at the expense of speed and performance. It was by far the slowest encoder. And another look at the encoding time results, this time charting performance by image with the average among all test images shown on the far right. If we think back, it's interesting to note that JPEG XL was the third most efficient encoder in terms of compression savings, while also being the third fastest. However, the JPEG XL build that I used in testing leveraged available RAM and VRAM the most compared to all the other encoders. So its speed most likely resulted in large part from it being optimized to take advantage of available hardware resources, more so than the other tested encoders. Let's now think in terms of higher level characterization. Based upon benchmarking results and documented designs, I've dubbed JPEG and JPEG LS, quote, early lossless, end quote, encoders. The gap in compression savings percentages by file between them is most likely due to JPEG-LS's ability to achieve more advanced and complete decorrelation through its use of the LOCO-1 algorithm for prediction, which also allows for residual modeling and context-based coding. Original JPEG, on the other hand, employs the simpler and less effective differential pulse code modulation DPCM predictive coding that is unable to attain total decorrelation of input data and involves no subsequent context modeling. Both codecs employed Huffman entropy coding during testing. Lossless JPEG 2000 and JPEG XR also share commonalities. Both employ either true wavelet, as is the case with JPEG 2000, or wavelet-like biorthogonal transforms, which use reversible integer arithmetic. Additionally, each uses unique internal color transforms aimed at better decorrelating the original RGB channels and improving compression efficiency and lifting schemes that significantly reduce computational complexity and increase performance. Both codecs also offer optional image tiling, which can increase speed and enhance error resiliency. JPEG XR was the fastest encoder of all the codecs that were evaluated by 9 seconds on average. These findings may be partially attributed to JPEG XR's use of a form of adaptive Huffman entropy coding. Though often suboptimal in terms of compression, Huffman coders are less complex and faster than arithmetic coders. Among this final group of encoders, I'd like to focus and close my talk with a few words on 2022's JPEG XL, which continues to gradually move its way towards a version 1.0 release. The codec's novel predictors, adaptive image-specific context modelers, and its use of the range variant of the recently introduced asymmetric numeral systems entropy coder have yet to be fully exploited as the standard is new and more mature encoders await development around the specification. Among the lossless bit streams examined, it is uniquely expressive and poised for future refinement through the adoption of techniques like AI heuristics. Notably, JPEG XL's adjustable effort feature, if Pareto optimized in an automated way for speed and compression density by individual image, holds the promise of a highly efficient, best-in-class, lossless compression scheme that can effectively leverage available hardware resources to work fast and at scale within production environments.